So there's that. So this is an important, important formula. If we have t squared times something you know how to take the Laplace transform of, then all you do is you take the second derivative of the Laplace transform of that function with respect to s, and that gives you the Laplace transform. So this is very nice. Anything we know, like sine, cosine, what's the Laplace transform of t squared times sine? You just twice differentiate 1 over s squared plus 1. So it would be something that's like 6th order in the denominator. It would be s squared plus 1 cubed that you'd end up with, something like that. That's fun. All right. Sorry about this part. This part of my notes I had a student type up over the summer, and I mean, the quality of the editing in here, it's not always uniform. Sorry about that. I mean, there are many true things in here, but there are also things like this. So, sorry I haven't had time to fix these things yet, but hopefully sometime soonish. So how would you calculate the Laplace transform of sine t cosine 2t? So for this one, basically, what you got to do is you got to convert it into things you know to take the Laplace transform of, namely sines and cosines. But you can do that with the imaginary exponential technique, for example. You can derive that sine times cosine 2t is actually 1/2 sine 3t minus 1/2 sine t. But these we can take the Laplace transform of. So the Laplace transform of sine t cosine 2t is in fact 1/2 of 3 over s. What the what? Come on. So this is obviously it's no bueno. This should be s squared plus 9, right? I mean, this is s squared plus 9, 3 over s squared plus 9, not s plus 9 squared. Dude, I want my money back. I paid the student money for these. I learned a lesson. Don't pay them until you check it. Let's see here. I don't know. This is so wrong in so many ways. There's a half that's missing here too. The spirit of the calculation is found here. Well, I do give partial credit. I'm afraid to look at the details of these examples now. This is e to the t for 0 less than 2, t greater than 2, right? So in terms of unit step functions, we turn it on at time 0, turn it off at time 2. And yeah, I think there's a parenthesis missing here, right? Well, this is right, anyway. Maybe you should just read your book here. I'm sorry. Oh no. I mean, I have the right ideas in these things, but the details are golly. So, to calculate the Laplace transform of this and that, we have to feed it through the thing that was about right here. This one is fine. That's just e to the t, which is 1 over s minus 1, right? But this piece over here, we have e to the minus 2s times the Laplace transform of not t minus e to the t, but I replace t with t plus 2, and then t plus 2 in the exponential also. This is much easier than the sine, right? If you have t plus 2 for the exponential, that's harmless. That just pulls down an e to the 2 times e to the t, right? So that's not as bad, but you should be aware of this. And so the answer is, this 1 over s squared, 2 over s, minus e to the 2 over s minus 1. So this is another, Laplace transform. All right, let me see if I can't find that one's, this, oh, look at this. Here's the t theorem in action. If you think about this, though, guys, it makes a lot of sense. How can we get like a fourth order polynomial appearing in a differential equation? If it's the significance of it, it's tied to the characteristic equation. Remember, it's only when we get to the quartic that we get like t times sine and t times cosine as solutions. So it makes a lot of sense that you need something like t times e times sine in order to get something that's quartic down here, because as you study examples, you realize the thing we're dividing by is the characteristic polynomial for the differential equation we started with. Let me get to an example here. I guess what I'm trying to say is for this chapter of the notes, look for strategies, don't necessarily look for details. All right? So these notes are very presidential. All right. Finally, an example. Not the one I want, though. All right. This example here, guys, is interesting because this shows you how to solve. So here, notice the initial conditions are at 1, right? If you have initial conditions at 1, you can convert it to initial conditions at 0 by making a substitution. You introduce y of t, which is w of t plus 1. So let's see, when t is equal to, goodness gracious, when t is equal to 0, we have w of 1, right? So for the y function, time 1 becomes time 0, basically, and then we can use the standard formulas. Everything is set up for initial conditions at 0 in the method of Laplace transforms, right? But that doesn't mean you can't use Laplace transforms for other initial conditions. You just have to run it through this substitution, right? So basically, you solve the problem in not the thing you're interested in, but in the thing you're interested in plus whatever you shift like this, and then solve the shifted problem, and then shift back at the end. This was very troubling to me for a while because when I was taught differential equations, this wasn't really emphasized to me. And so I thought, why are we learning this method of Laplace transforms? It's so handicapped. It only works when the initial conditions are given at time 0. What about other times? Maybe I want initial conditions at time 3. Then this method is useless. No, I wasn't taught how to make it useful at other times. You just shift. It's not a big deal, really. Just like this. So like here, after you make the shift, the shifted differential equation is y prime prime minus y equals a sine t. Then you Laplace transform. You get this. I'm doing some sneaky algebra to do the partial fractioning. Inverse Laplace transform gives you this. And then at the end, my wt is what? Wt is, did I ever write it anywhere? If y of t is wt plus 1, what's w of t? Y of t minus 1, right? So I take y of t and I replace with t minus 1, and that gives me the w of t. See? Just like that. So I may have forgotten to, but I usually try to assign one of these somewhere. I may have forgot this. I may have forgot for you guys. If I did, will you forgive me? Yeah. Okay, cool. Oh my goodness. Non-constant coefficients are ugly in any formalism. See, if you have coefficients for your differential equation which are not constants, what ends up happening to you when you transform through it, you end up with like a differential equation in the frequency domain, which then you can solve because this is differential equations. And yeah, so this example is, maybe we'll work through it another day. What I wanted to show you was an actual honest to goodness discontinuous problem here. Sorry, look away for a second. I forgot to warn you, Dramamine issues. Come on, tell me I don't have an example in here. Just a second. Ugh. I can't see anything anymore. I'm trying to find like I think test 3 solution would do it for us. I'll have one in there. Ugh, maybe not. Ah, worthless. Do you guys see test 2 solution? I'm looking at it, I just don't see it yet. When did I cover Laplace transforms? Man, I'm sorry, guys. Just trying to find you guys an example that would be good. Nah, let's call it a day. Extend early first change. Anyway, I try to show you guys more examples next time we're here. So, thanks, guys. Have a good break. Yeah? Oh, yes, thank you.